Okay, good evening, everyone. Welcome to lesson number 3. Basically, tonight we're going to be talking about simulating rocket performance, which is typically what you want to do before you build a rocket, just to make sure that you're on the right track. On the other hand, before we do any new material, I want to turn this over to Sophia. She may have some comments and some questions and maybe run around the room or not. So I'm just gonna, you know what? You've got your own video camera. Why don't you just use your video camera? On the other hand, here's a question. What are we doing for audio? You need to use audio from my mic. If so, maybe I should use this one.
Yeah, we can use that one. I'll just turn
Okay, great.
it. Can you all hear me? Yeah. Okay. All right, so I have gotten schedules from everybody so far, so thank you for passing those along, and I think I got feedback to everybody. I think a common thing we saw was a lot of people, you would put the generic name of the step, like assemble motor mount, assemble fin can, which we were kind of looking for a little bit more detail, just so members of your team, when they look at that schedule, they can have a little bit deeper of an understanding of what exactly goes on for each step, as well as gauge maybe how long it would take them to complete that, what sort of epoxy work they might be doing, that sort of thing. It's also very helpful when doing the dates to consider appropriate drying times. So some of them you might want to leave it overnight. Some of them you could do in the morning and then do at night, depending on how condensed you need your schedule to be. So definitely make sure you are accounting for those drying times in your dates. I'd also suggest, oh wait, is somebody asking a question?
Nope.
Okay, cool. I thought I heard something. And then additionally, I would say it's also very beneficial in your schedule when you're maybe writing out specific steps, putting maybe special notes. I know some people, they would put warnings in bold or red, such as when it came to the order of epoxying certain parts, or making sure you epoxy the root edge of the fin onto your fin can. Those sort of things that if you're not really paying attention, you could very easily mess up. So it's just kind of reinforcing that and making sure you don't miss that when you're just briefing over the instructions.
Do not disturb. That's the most important sign to put on your stuff.
Yes, exactly. And you always want to put, a warning if you have wet paint or wet epoxy. So you don't want people to touch that, especially if maybe you are sharing a lab space with a lot of other teams who may not know exactly what you are working on. But yeah. And then I can talk a little bit about what I've been up to. Some of you, I've seen you pop onto the build slides. And I've continued to add to those as I go on. So last week I had the aft thrust ring and the rear centering ring on my motor mount. And right now I have my fin can just about done. So you can see I added a epoxy fillet down here between the rear centering ring and the motor mount tube, as well as fillet right above the top centering ring and right below it. I also started to do one of the fillets, one pair of the fillets for the internal joints here. Can kind of see them. Yeah, so I use the tape method for this. Not super necessary since they are going to be inside the rocket, unless you want it all to be very pretty and smooth. So I did this earlier in the morning. So right now it's fairly dry. I will probably just let it sit overnight before really playing with it. And then as you can see, just a little demo. I have not done epoxy on this side yet, but this is how I would tape it. So basically, really the only thing I'm exposing right here are the joints. So I can just mix up epoxy, slap it on there, and use a small popsicle stick to smooth it all the way down. You want to make sure there's no bubbles, no gaps. Yeah, and then you definitely want to take this tape off before the epoxy dries. Otherwise, you will be struggling to get all the tape off nicely. Yeah, and then I have the eye bolt on there as well. And while that was drying, I actually started to work on the avionics bay. Some of you asked me at what point should you assemble the avionics bay. You can assemble it at any time that fits into your schedule, as long as it is before you do all the recovery attachment points. So maybe when you're waiting for your fillets to cure, you can take care of some of these steps first. So as you can see, I epoxied the coupler tube into the smaller chunk of airframe here. One thing I really learned the hard way was that the fit between the airframe here and the couplers is very, very tight. So when you're dry fitting, you might see you really have to be careful, and you might have to push a little bit to get it to fit in there. So I would suggest doing a little bit of sanding to make sure you can nicely fit it in there. Obviously, you don't want it to be too loose or too uneven, but you also don't want to be struggling to get it in there, because for me, I did a little bit of sanding, but then once I put the epoxy on there, it was a real struggle to get it all the way in. So I would say, mix up a fresh batch of epoxy that's still relatively smooth and not tacky. That way it's also a lot easier to slide your coupler tube in there. And then I also started to work on the bulk plates here. So for this, all you had to do is glue these two plates together. And you also see, I didn't put this in yet. You have to keep these holes clear, because eventually you will be putting an eye bolt and then your threaded rods in there. So when I was gluing them together, I was sure when I was spraying the epoxy out, I wasn't putting it too close to those holes. And when I squeezed them together, if anything did come out, I just used like a Q-tip to just clear it out and make sure it did not cause problems for the future. And then, as you can see here,
Can you remind me, why is that end bulk plate double thickness?
so your bulk plate acts almost like a cap for your avionics bay here. So you'll have your electronics in here, and this will pop on right here. And then you will have your wires coming out of these holes here to your ejection charges. And basically you don't want all that stuff happening right by your electronics. So by having these end caps, we can protect our electronics as well as keep pressure regulated.
Okay, so those are self-centering, which basically means that the smaller piece goes inside the tube, and the other piece goes against the tube, but inside the airframe.
Right.
Looks like a little more sanding might be in order.
Yes.
Okay.
Yep, and then eventually the airframe should fit over nicely, but again, very tight fit on all of these parts, so we're gonna need a little bit of sanding. I think that pretty much brings us up to speed with what I've done.
We were about to talk about the notches there.
Yes, and then since I have done the fin, or some of the fin can already, you can see I had to make those notches with an X-Acto knife to be able to slide it out. Just be careful as you're doing that. Yeah, you're not scratching up the aft thrust ring too much. The small box cutter that's included in your kit is really nice, and it's nice and sharp, so just carefully take that to cut out the slots. You'll also want to make sure you're drawing this line that your rail button will go on eventually, and make sure you also get that mark on your aft thrust ring right there. So then when you put it back all together again, you know exactly how it was epoxied in originally.
And then can you show us the end view of your eye bolt there? Just make sure that it does not interfere with the tube at all.
Right, it does not interfere with the tube. You also want it to sit between two fins here. So
show us the end view.
Oh, I'm sorry.
The camera. Other way, other way.
Oh!
There you go. Perfect.
Yeah.
So the airframe will slide over that without striking either the eye bolt or the recovery harness that you're going to tie to that eye bolt.
Right.
Don't forget to tie that on.
Yes. So you want to tie that on before you glue everything into the airframe. Yeah. I think that brings us up to speed.
Okay, great. I think we better pause for questions because we're going to go in a completely different direction in a moment. But if you have questions about building, what she has done, what you need to do, now would be a really good time.
So I have a question. When do we need to take photos of the steps for the safety inspection at the end? Are we supposed to be taking photos of the fin can? And
Yes, I would say taking photos of especially these epoxy joints would be a good idea.
okay,
Yeah, I think those are important, as well as we can make sure things are glued in the correct place. Making sure you have these sorts of eye bolt joints and recovery attachment points where they're supposed to be.
So Steve put into the chat, are the rail buttons supposed to be screwed into wood of the centering rings or just through the tube wall anywhere? And the answer is not anywhere.
Yeah. Yeah, so looking at the rail buttons here, you can screw them through the airframe.
Hold them out so people can see what they
Yeah.
look like. They probably haven't played with those parts.
Let me get those if I can. Then there's, okay. So,
I'll open up the camera.
so you see you will have a screw. Oh, I can't see myself. Oh, here it is. You'll have a screw. And then you have the actual rail button, this little black plastic part, and then a weld nut. And so what will happen is the screw, a hole for the screw will need to be made into the airframe. Oh my goodness. They're also very little and hard to handle. But you'll need to make a hole into the airframe tube, and this rail button will go through the airframe and then attach to this weld nut right here.
So I think you might have that backwards.
Okay.
Basically, pardon our delay here. This goes inside and this screws in this way.
Yes, you're. My apologies. This goes on the inside. Very tiny, like I said. And then screw it onto the screw. Oh my goodness. Oh my goodness.
But anyway, to your question, one of these rail buttons should be placed essentially as low as is practical. And the second one should be placed essentially as at the center of mass or center of gravity of the rocket, which will be somewhere partway up, maybe halfway up or so. And you should not place those until after you've done simulations, because simulations will tell you where the center of gravity is likely to be. So the rail button is on the outside, and you don't want to actually screw that in so tightly that it can't spin. The idea is it's actually supposed to roll along this rail. So the weld nut goes inside the airframe and pokes out the side, and then the rail button goes over the top of that, and the screw holds it in place. So the one that's close to the center of gravity can probably be placed rather late in the build process. However, the one that's low down will be part of the fin can assembly, and you need to make sure you can get that in place prior to closing up the fin can, because once you close it up, you can't reach in there anymore. Another possibility, which is not, it's possible, is to screw these things into, the airframe is not tough enough for you to screw into it only. So then you want to screw into a wooden piece, in this case, a centering ring that's underneath the surface. But this particular kit is not designed for screwing into centering rings. So the answer is not screwed into centering rings and not just anywhere. You have to be careful about the placement of these two things. Other questions? Okay, as you have more questions, by all means, bring those to our attention. Why don't you send me my camera back here? So let's dive into sort of the details for new stuff for this lesson. First of all, let me point out the homework. So essentially the homework for this week is to look at chapters 5, 6, and 7 in the high power rocketry book and chapter 21 in the model rocketry book. Basically, the high power rocketry book, for some strange reason, doesn't really talk about simulation software. And so you really need to go back to the precursor book, which is the more serious of the two books, in fact. So look at chapter 21. We will be using a software package called OpenRocket, mostly because it's free, but that chapter will talk about RockSim, and you're certainly welcome to purchase RockSim if you want. OpenRocket and RockSim are very similar, except in price. So the exercises will be to look at the rocket motion slides in more detail. I'm going to show those to you in a moment. And then to download OpenRocket and make sure that somebody, maybe more than one person, gets pretty good at using OpenRocket and at simulating things. Okay. And so we'll be flying on an H225 White Thunder motor. And so that's the motor to be regularly asking OpenRocket to put into the rockets that you sim. But it has libraries of many, many motors inside of the software. And then, of course, you'll be continuing your building. And then there are links to where documents are posted, including this one, and Sophia's build instructions, which have grown a lot since the last time I looked. Fine. So here's just a few more concepts and vocabulary. We're going to use a flame protector to protect our parachutes. A different possibility is a piston. So a piston actually is essentially a piece of coupler tube, which is completely blocked off with a bulk plate. And the idea is you place the parachute on one side of it and you have the explosion on the other side of it, and that thing will slide like a piston. It's a cool device, but it only works sort of once. And if we fly our rockets only once, that's probably fine. But we're actually going to use flame protectors because they can be used over and over again and even moved from rocket to rocket. Another option, which is typically only used for model rockets, is this cellulose fluff. People call it rocket bark. So you might come across that, especially when you're at a Tripoli launch. If you watch model rockets, they tell people, don't use the wadding that came with the model, use rocket bark instead. I think it degrades in the environment more quickly. Remember that we're going to be putting two parachutes in, a drogue parachute, typically a pretty small parachute. We'll pull that at apogee. And then a main parachute, which will pull as the rocket gets closer to the ground. You have both parachutes in hand, although I'll tell you right now, the main parachute is probably oversized. I just gave you one that I happen to have around. And so if you really want to, you could potentially use a smaller main parachute, but there's not that much utility in doing so. The reason we do this dual deploy is to allow the rocket to descend more quickly and hence not drift so far. So we're trying to minimize how far it drifts before it lands, and we don't have to hike so far. You'll see that in the simulations in a moment. So there it mentions RockSim, which costs maybe $100 or so, OpenRocket, which is free. I'm not even sure the current version of either one. It used to be RockSim 9 and OpenRocket 10.3, but it may be more higher numbers now. We'll see in the simulation software the idea of a parent-child relationship in a moment. And also we'll see, I'm going to demonstrate this, the fact that sometimes you need to add weight to your rocket to make sure that it has some chance of flying successfully. That sounds sort of counterintuitive, that the heavier rocket, the higher it flies, but in fact that is true. If a rocket is unbalanced, it won't fly high at all, no matter how lightweight it is. We'll look at plotting options. We'll look at wind cocking, which boils down to how much it cocks into the wind and hence how far it ends up landing, moving away from you laterally. And then looking at graphs that get plotted on top of each other. So there are just a few concepts, vocabulary. Now what I'd like to do actually is to step through some slides. I'm going to call these rocket motion slides. These are slides that I put together for a class. That's why it says AEM 1905 on the top there. So very quickly, this is physics now, talking about calculating the motion of a rocket undergoing purely vertical flight. So frankly, there's a bunch of simplifications going on, including no sideways wind. I think it's best to think of the rocket, this kind of rocket at least, as traveling in 3 different phases. The first phase, the boost phase, is when the rocket motor is firing. So the rocket is picking up speed, going upwards, it's accelerating upwards. It's actually losing mass, okay, at least some, because the motor is burning. And then eventually the motor burns out. And then that's the end of phase 1. And at the end of phase 1, you're high off the ground and you're traveling very fast vertically. And then phase two is the coast phase. That is when you continue traveling vertically and eventually stop going up, okay? And so the motor is burned out, so the mass is now fixed, but you're going up. But now you're accelerating downwards, you're slowing down. And then the descent phase, presumably at apogee, perhaps you'll pull 1 parachute. And so now you're coming down, but it's a completely different shaped object. It's no longer streamlined. It's got this parachute out. It's trying to sort of maximize its air resistance. The mass is fixed, and you will eventually start coming down at some probably terminal velocity. And so in this case, the acceleration is actually 0. So frankly, if you studied physics and they talked about what to do under constant acceleration situations, this is the only one that you have any chance of solving. That's kind of why people make this joke. It's not rocket science, or it is rocket science, or whatever, because doing calculations for rocketry are difficult because it's not constant acceleration. So this is just a refresher. If I use the following variables, x being the position, in this case, the height, above the ground, so up will be positive. V is the velocity, in this case, for vertical flight. We could think of that as just the upwards speed. Acceleration, that's the rate of change of velocity. T is time. And so in the case of constant acceleration situations, of which we do not have many here, but if that were true, your velocity at some time t would be related to your initial velocity plus a times t, because a is telling you how quickly your velocity changes and t tells you how long it's allowed to be changed. And then your position at some time t will be calculated as your initial position plus your change in position due to your initial velocity plus 1/2 at squared, which compensates for your change in position due to the fact that you're accelerating. But as I mentioned before, this motion is rarely constant acceleration, so there's some limitations to what you can do with these equations. On the other hand, Newton's laws, called the laws of motion, basically say that forces can explain motion. So in particular, if you can understand the total amount of force, the net force on an object, you can figure out its acceleration, if not for a long period of time, at least instant by instant. So here are the 3 phases. In the first phase, you have a thrust, which is pushing the rocket upwards. It should actually be drawn longer than that. You have a gravitational weight, which is pulling the rocket downwards. You'll have a drag, which is air resistance. So that will be defined as something that goes along the axis of the rocket. And then lift, that will just be an air force, but it's going to be sideways to the rocket. And in this simplistic case, I'm going to ignore the possibility of sideways forces. So I'm just going to be comparing weight and drag and thrust. Weight will be diminishing slightly because you're burning fuel, so you're not as heavy. Drag will be increasing dramatically because you're going faster and faster, and drag, air resistance in this case, depends strongly on your speed. And thrust will be maybe constant and maybe not, depending on what your motor is. In phase 2, you have exactly the same forces, except now you don't have any thrust, and your weight is going to be fixed for sure. And then in phase 3, it looks very different. You have a downwards weight, you have an upwards drag, and no thrust at all. And the object that's causing the drag will be the shape of a parachute, basically. And so that drag is likely to be rather different in size as a function of velocity. Here are Newton's 3 laws. Basically, the first law says, if the forces when added together as vectors give you 0, then your velocity will be constant, okay? And then Newton's second law says, as long as mass is constant, your acceleration, which is a change in your velocity, can be figured out based on summing the forces and dividing by the mass. Sometimes this is written as F equals ma, or sum of F, net force, equals mass times acceleration. It turns out that's not how Newton wrote it. Newton said forces explain changes in momentum, and momentum involves both velocity and mass. And so forces can explain changes in velocity, or forces will be influenced by changes in mass. And then Newton's third law just says that when two objects interact, both objects get forced in opposite directions, but the force is the same size. Okay? So again, probably old hat to almost everybody on this call. Notice that these forces are acting on different objects, so they won't ever cancel out in the case of Newton's third law. So here's some analysis of phase three. This is the easy one. In phase three, basically, if you think of your object, your mass of your rocket, there's a downwards weight force, which is constant. There's an upwards drag force, which once you reach terminal velocity will also be basically a constant. These will match, so they add to zero, so the acceleration is zero because the net force is zero. And so in this particular case, you can say, look, the weight is related to your mass times g, and the drag is related to your velocity squared times the density of air. Can you see my cursor on your screen? Okay, the density of air, the square of the velocity that you're traveling through the air, and then two constants. One is related to the area, cross-sectional area of the object, in this case, the parachute, and then the coefficient of drag of the object, which in this case is also a parachute. And so knowing something about your parachute, like a circular parachute with diameter such and such, you can figure out its area. The coefficient of drag for a parachute is kind of known. It's typically some number between 1 and 3. And so you have options here. One option is to solve for the terminal velocity in terms of things like weight and area of parachute and coefficient of parachute. Another possibility is actually to use a desired terminal velocity and solve for the area of the parachute. In other words, use this to help you choose your parachute. So in our case, you're sort of given a parachute, but this is what a simulation will do for you. You state the parachute you're going to use, and it will calculate things like how fast you will ultimately be traveling and ultimately hit the ground. That's the easy case. Here's the second easiest case, and that is where there's no thrust. So in this case, notice that you have a mass, but the only forces acting on it are downwards. There's a weight downwards, that's the weight of the rocket, and then there's a drag force. This is essentially related to the frictional force on the rocket, but it turns out that this is highly dependent on your speed. And so as you coast from very fast to not moving vertically at all, this force will go from very strong to zero over the course of the coast phase. You can still do some calculations here. So for instance, in this case, the drag is related to the density of air, the speed of the rocket, which is changing, the cross-sectional area of the rocket now, not the parachute, and then some sort of a coefficient of drag for the rocket, which might be possibly fairly small because this is a streamlined object. In fact, if you were so bold as to pretend that there was no drag at all, see, the drag is likely to be small, then you could even calculate approximately how high you would get, starting from some speed at the end of boost and how high you could possibly get. So for instance, if we neglect drag altogether and say that we need to change our speed from maximum speed at the end of boost to zero at apogee, you can actually calculate how long you coast. And the answer is you coast approximately your maximum speed at the end of boost divided by g. And then you can calculate how high you go, at least how high you go above the end of the boost phase. What will happen in the case of a simulation program is it will do this calculation, but it will do it in very small time steps, during each of which the drag force, for instance, is approximately fixed because the velocity is not changing very much. Here is a more realistic version of the first phase. Notice the thrust vector is very big. You have a large thrust vector. You have a downwards force, which is increasing as you pick up speed, and a downwards weight, which is actually decreasing as you burn fuel. But in fact, you don't burn a lot of fuel in these rockets, so that's almost fixed. This, on the other hand, is going to be increasing a lot, and this thing might or might not be fixed depending on the motor that you use. Okay, so here, again, if you were to pretend, for instance, that you don't have hardly any drag, you might be able to make some progress in figuring out approximately how high you would get, especially if you know things like how much thrust you have and how long the motor will thrust for. But notice in this particular case, the net force would be T pointing upwards minus drag minus weight, those are both pointing downwards, and that gives you mass, which is actually changing, times acceleration, and thrust is not really fixed, and drag is very much not fixed, and weight is not fixed, and mass is not fixed, and so acceleration for sure will not be fixed. So it's hard to make a lot of progress with these equations over the whole phase one, but you can maybe make some progress over little bits of phase one. I'm going to skip this, but you shouldn't actually. This is talking about how a rocket actually burns and some of the rocket equations that are behind it. I want to go straight to a graph though that shows some information for a specific motor. So this happens to be an H125 motor, H class 125 average thrust. And notice that this is time versus thrust. And so I noticed that it takes a little bit of time for the thing to start thrusting. There is actually an initial spike. This is fairly common. And then the thrust goes down for a bit and then it grows back up again. And so the maximum time of maximal thrust is about 1 second into the firing here. And then, so this is called progressive. There's more and more thrust as time goes by. And then regressive, slightly less and less thrust. And then eventually the motor pretty much burns out. And we're going to call the 5% of maximum the start time and 5% of maximum the end time. So this will be the duration of the burn from here to here, even though there is a little tiny extra burn after the end time, and there's a little tiny extra burn after the beginning time. The area under this curve is referred to as the impulse. And so the key is you want to watch for the impulse of your motor, and that will, and then for instance, if I were to make a box that goes up at this point, straight across at some average thrust value, and then straight down, that will give you the same area, okay? So this particular motor has 12 seconds right here of delay grain. 125 is the number of newtons for average thrust, and 266 is the amount of impulse. So here are the impulse classes. So basically, H motors are from 160 to 320. Newton seconds are the units. So this particular one here is 266. It's kind of right in the middle of the H class, okay? But then by the time you double your impulse from 160 to 320, then 320 to 640, that would be an I class motor, and then 640 to 1280, a J class motor, et cetera, et cetera. So when you see a motor, here's how it might be described. Cicerone is the manufacturer. Pro 38 is the diameter in millimeters. 266 is the impulse in Newton seconds. H is the impulse class, so there's some overlap, but this number tells you exactly the impulse, and this just tells you the impulse range. 125 is the average thrust, and then 12 is the number of seconds for the delay. The delay grain, how long does it take to explode after it finishes burning? H and I motors are called level 1 motors. J, K, and L motors are level 2 motors, and above that is level 3, and so forth. There actually is no level 4. Pretty much you're allowed to fly anything within reason once you have a level 3. My certification is a level 2 certification. I encourage you to spend some time on the rocket equation. I'm not going to right now. I do want to talk about graphs. In particular, I want to talk about graphs that look like this. This is actually very typical and frankly, kind of hard to read. This is a graph that's trying to show you all three, the acceleration, velocity, and position, altitude, as a function of time on a single graph. So sometimes they're in different colors, but this here shows that this rocket, over the course of maybe 12 seconds or so, goes from 0 altitude above ground level up to just over 3,000. So these numbers are the altitude above ground level of the rocket as time goes by. So this is the altitude graph. Notice that it peaks here at about 3,060 feet. And then just after apogee, it actually pulls a parachute and then it starts to descend at a completely different rate. And notice that at the end of 60 seconds, it's still 2,500, 2,200 feet up. This hasn't landed yet. It's going to land much later in time. On the other hand, on the same graph, I have velocity. So the velocity, which is going to use these numbers, which are going to be in feet per second. The velocity starts from 0 and eventually peaks up at about 550 feet per second. And then the velocity, that's the end of phase 1. And then it slowly decays away until it reaches slightly negative velocity right here. It's on its way down. And then it actually will continue at a slightly negative number That's not shown in this graph. And then acceleration in G's, okay, basically while it's burning, it has a positive acceleration, perhaps in this case about 25 G's, and then it burns out. And so after it burns out, the acceleration will be 1G, I guess, downward, negative 1G. That's also not shown on this particular graph. But trying to be able to read graphs that have multiple things, usually as a function of time, with multiple scales, is, well, that'll live with it, shall we say. But that's part of the deal here. So what I want to do now, for just a few seconds, few minutes, is I want to show you one of these simulation packages. So I'm going to show you Open Rocket. So here's Open Rocket. If I can get it to open. Wake up. There we go. Okay, so what we're going to do is we're going to draw a rocket down in this area, and then we're going to do some simulations with it. So the first thing I'm going to do is I'm going to just open a recent rocket that I was playing with. Let me take a look at this Hawk. Okay, so this rocket is unusual. It has really big fins. A few things that I want to point out about this rocket. First of all, this dot here is the center of pressure, and this dot here is the center of mass. And remember, for a rocket to want to fly forward, the center of mass has to be forward of the center of pressure. And notice this one is already backwards of it. So its stability is negative 0.286 calipers, which is basically 0.286 diameters. Notice that they're not even a full diameter apart. This is a problem. And of course, if I add a motor, it's going to get even worse because the motor will weigh down the back of the rocket. So for instance, let me just put a motor in this one right now. Notice how close together these are, and watch what happens when I add a motor. Select motor. I'm going to say H225. There it is, Cicerone. Okay, boom, I added the motor and suddenly the center of gravity is even farther back, even more unstable. This would be a bad day. So if I were to try and take this rocket, let me actually try to fly it. So I'm going to say flight simulation, new simulation. The length of the rod is 72 inches at Tripoli, so that's, I want to be realistic there. And I want to simulate and plot what would happen if I fired this rocket, unstable though it may be, and it's ready to draw a bunch of graphs for me. Here's altitude versus time, vertical velocity versus time, acceleration versus time, and I'm going to ask for one more. I'm going to ask for lateral distance. How far is it from me sideways versus time? And I plot it. And it's a mess. First of all, it only goes up 250 feet or so. And although it's burning, it's doing all sorts of bad. This rocket is more or less tumbling. Okay, so this was a bad idea, but I can fix that. Here's how I'm going to fix it. I'm going to put into the nose cone of this rocket just a piece of ballast, a chunk of mass, so as to draw this point forward of this point. And then I'm going to relaunch it, and you'll see, even though I made it significantly heavier, it actually started to fly properly. So I'm going to go back to rocket design, and I'm going to say into the nose cone. So the nose cone is the parent to a bulkhead and an eye bolt. The body tube is a parent to the fins and many other things. Into the nose cone, I'm going to add just a mass component, a chunk. I'm going to call this ballast. Ballast. There we go. And watch the center of mass as I increase the ballast. See how it's moving up? Basically, I'm going to do this. I'm going to keep clicking until I get my stability to be above 1. It's up to 1.2 right now. Of course, I don't want to put my ballast outside of the nose cone, so I better move it to be at least inside of the nose cone. There it is. And my stability is still better than 1. I want my stability here to be between 1 and maybe 3 or so. So this is a much healthier rocket. Okay. Let me check one more thing. Here's the parachute. And if I say edit the parachute, I'm going to find out when is the parachute going to come out. And the answer is I'm going to change this to be come out at apogee. Okay. Close. So now I've modified this rocket and I'm going to fly it. So I want to do a new simulation, set my launch rod to 72 inches. You know what? I'm even going to beef up the wind speed, maybe to 10 miles an hour. That will make it drift somewhat farther, just for fun. Simulate and plot altitude, velocity, acceleration, and lateral distance plot. Oh, this is way healthier. So the idea is now the rocket went up to over 2,000 feet, about 2,400 feet, and then came down at a constant rate. And then the velocity increased and then diminished. The acceleration was very strong and then pretty much went away. And notice the lateral distance. This is interesting. It drifts away from me and then it drifts back over my head. So here it's several thousand, it's over almost 2,000 feet up, but it's not far from me. It's straight above me. And then it continues drifting and it lands maybe something like 1,000 feet away from me, 1,000 feet right here. So that would be a bit of a hike. On the other hand, if I take a look at this, I'll notice a few things. One is I notice it leaves the rod at 70 feet per second. That's actually good. I want that to be more than 45 feet per second. That's kind of a rule of thumb. Maybe write that down, 45 feet per second. You want to be off the rod at least that fast, because your fins don't actually catch air and do the things they need to do for you if you're traveling too slowly. Similarly, I want to hit the ground at, ooh, this is just marginal. I want to hit the ground at no faster than 25 feet per second. Again, another rule of thumb. So this one is just barely true. Watch what happens if I do the following. I'm going to go to that parachute and I'm going to edit the parachute and make it smaller. So your parachute for your apogee parachute is actually 12 inches in diameter. So I just took a 3-foot diameter parachute and made it a 1-foot diameter parachute. Close. Simulate the flight. New simulations. 72 inches. I wish this would stick, but it doesn't. Simulate and plot. I didn't bother to beef up the wind speed. Okay, so now it's coming down faster. You can see this slope is more steep. And it's landing at 72 feet per second. That will definitely break something. Okay, so that was the wrong size parachute. Here's how you can kind of tell if your parachute has any chance of being right. Make sure your hit the ground speed does not exceed 25 feet per second, maybe even is somewhat less than that. And your leave the rod speed is at least 45 feet per second or more. Okay. So the last thing I'm going to do, literally for about 5 minutes, is I'm going to start drawing your rocket. And then I'm going to post what I drew. And I'm going to say, look, you can start with this. Why don't you finish this up and make more details and get somebody on your team, at least one person, to be pretty familiar with OpenRocket so that they can keep working on this. So here's what I'm going to do. I'm going to just start a new rocket. And I'm just going to build it kind of from the top down. So the first thing I need is a nose cone. And I'm going to go and choose a nose cone from a database. And maybe I will choose, I want a 3-inch diameter nose cone. This is a 3-inch diameter rocket. There's a nose cone that looks like a 3-inch diameter. So here's a question for you, Sophia. Why does this nose cone not have a shoulder on it? Did I just choose the wrong one? I'm just surprised. I thought that it would come with a shoulder.
No, the default is 0 shoulder.
Default is 0 shoulder. So I'm going to go back and edit that, and I'm going to make sure it has a shoulder. Ah, there it is. Length of shoulder 0. So I want the diameter to be what? Something like,
Just a smidge smaller. So
I think it was a 3.1-inch diameter. So this is 3. No, we'll try it. And I'm just going to beef up there. Oh, that was bad. So now here's another problem. So I'm asking her to help me out here. I thought I chose a 3-inch diameter nose cone, and yet obviously it's not 3 inches in diameter. It's only 1.9 inches in diameter. So I clearly chose the wrong nose cone. So I'm going to delete it, and I'm going to ask you for advice. What should I choose instead?
so
So this is the one I was looking at. Let me try this one instead.
yeah.
Okay, and I will.
Could you go to general? Yeah, so base diameter, it says it's 2 inches. Not sure why.
Okay, definitely I want that to be 3 inches.
Right.
Fine, and this is probably not the right length either. So you're going to have to actually keep working on what I've done here. This nose cone is not going to be made out of cardboard. It's going to be plastic. And let me just make sure I have a reasonable diameter. Let me call that 2.9 inches. And I'm going to make it stick out. That's sort of what your nose cone looks like. Maybe make it a little bit shorter. I would suggest that you try to make something that reasonably looks like a nose cone. And notice that a nose cone, by definition, is unstable. But don't worry, I'm not planning to fly the nose cone by itself. Okay, so next up, I need to add to the nose cone a body tube. Okay, so there it is. It has guessed that I've run a body tube that fits the nose cone, which I do. On the other hand, my upper body tube is going to be more like about 16 inches, I'm guessing. And this body tube will be made out of phenolic, close. And then beyond the body tube, I'm going to add a coupler. And so the coupler will fit inside of there. And I know that your thing is 12 inches long. It's a tremendously long thing. And I'm going to, oh, that was the wrong story. Not outer diameter. That was the wrong thing. I want the length. Here we go, length, 12 inches. And I want that to stick out the bottom about halfway. So let me have it stick out 6 inches. I'm not even bothering with the collar, okay? And this also would be craft phenolic. And then the next thing I'm going to do is I'm going to choose another body tube. This is going to go down below the first one. And let's say that that's about 30 inches long or so. Also made of craft phenolic. Good. And notice it still is calculating all of the things, like its center of pressure is still way up here because none of these tube sections even impact that. The center of gravity on the other end is way back here. This is fine. Now, associated with this body tube, I definitely want to have some fins. So let me just say that I'm going to have trapezoidal fins. I'll have 3 of them. Let me make them a little bit taller than that. Let me make them a little bit longer than that. No, that's not even too terrible. You should make these fins realistic, okay? But this is about what the fins look like on our rocket. Of course, the fins on our rocket are made of wood, so I'm going to choose maple, and I believe they're 0.25 inches thick. Fine. So I'm making progress. This is not exactly right, but if I give you this model, you can tweak the details of it to make it exactly right. Now I'm going to actually put inside of this body tube an inner tube, and I want the inner tube to be a motor mount tube, okay? And I'm going to choose a motor mount tube from the database. So what I'm looking for now is a 38 millimeter motor mount tube, maybe this one here. Let's see if that works. There it is. Aha! Now I don't need a motor mount tube that's 48 inches long, but excepting for that, I think our motor mount tube is about 8 inches long or so. And it's actually not vulcanized rubber. I think that's also probably phenolic. So there it is, close. Now what I should do is I should put some centering rings to hold that motor mount tube in the center. Okay, so here we go, centering ring. And let's say that my centering rings are made out of wood and they're about 0.25 inches. And there's my centering ring. I just need to place one close to the top. Actually, I'm going to place one close to the top of the fins, right about there. And I'm going to make another centering ring and place that. Same details here, 0.25, made out of wood. And I want to place that, oh, that was in a good place, already way at the bottom. So there I have, oops, you know, I can actually type this in. I don't have to fiddle with my sliders. So I have 2 centering rings holding my motor mount tube. Now I probably should put in a parachute. So inside of this body tube, I want to add a parachute. And just for fun, I'm going to make it a 12-inch diameter parachute, which is too small. I'll tell you that right now, okay? And this parachute will be located approximately at the top of the motor mount tube. Basically, the parachute will slump down. to here when you fly. So that's an appropriate location for it. So that's fine. I'm also going to put inside of the body tube some shock cord, retention harness. This will be tubular nylon. It will be about 12 feet long or so. And I'm going to put that also down here close to the parachute. So that's a sort of an approximate place. And notice as I move that around, it moves the center of mass around because this is a fairly heavy object. That's fine. And then the last thing I'm going to do, just for fun, is I'm going to put some mass inside of the av bay. And the reason is we're going to put electronics and batteries and stuff in there. So there definitely is going to be mass inside the av bay. The av bay is this tube coupler. So this should be part of the upper body tube mass object. I'm going to call it av bay electronics. And I'm going to say the mass is maybe 6 ounces. And notice that as I put 6 ounces, oh, but it's drawn it way up here. I need it to be right about the middle of the av bay. That's a more appropriate place for it. So I'm okay with that. And I look at my stability. My stability is 1.5. That's not terrible. Okay, basically, the center pressure is about 1.5 diameters behind the center of mass. And if it wasn't true, I could add extra mass. And in fact, when you build it, you should check things and make sure that things are coming out and add extra mass if that's what it takes. So let's go ahead and fly this. Why not? Motor configuration. I'm going to say a new configuration, select motor. Let me go for that H25 again. Okay. So, ooh, this is bad. What happened to me? What went wrong? Who can see it? Something went wrong. Sophia, you see it?
I see it.
What is it?
The center of gravity was pulled back.
Yes, my center of gravity moved backwards naturally, and it now is right on top of my center of pressure. So my stability is no longer 1 or greater. In fact, it's slightly negative. Okay, so here's what I'm going to do. I'm going to go back and I'm going to increase the mass of my av bay electronics. Why not? Okay, I just need to increase that enough to bring that forward a bit. Maybe I don't really want to put 26 ounces in my av bay, but I need the thing to be stable. Okay, fair enough. So that was unrealistic. If I had put my extra mass way up here, I might have been able to get away with less extra mass to increase my stability. So here we go. And my parachute, what did I decide to do with my parachute? Oh yes, I want it to come out at apogee. There it is. And let me simulate this flight, new simulation, 72 inches here. Why not have 10-mile-an-hour winds? Why not? Simulate and plot. There are my 4 plots. And I plot it. And it goes up to almost 2,000 feet. That's not terrible. Okay. On the other hand, it drifts away from me and lands over 1,000 feet away from me. That's a bit of a hike. Frankly, and let me actually look at hit the ground velocity. What do you think about that, Sophia?
Oh, that's pretty bad.
That's very bad.
Yeah.
That's way too fast. This is coming down way too fast. Okay. So on the other hand, leaving the velocity off the rod, that's okay. So here's what I'm going to do. I'm going to go and I'm going to add a second parachute. So I'm going to put a second parachute in the upper section. And I'm going to make this a 4-foot diameter parachute, monstrous parachute. And I'm going to say it's going to come out at 500 feet above ground level. Okay. And I'm going to place it right here at the top of the av bay. There's a bulk plate here, so it can't be lower than that, but it needs to be in this section. So that's a realistic place for it. And, you know, probably I ought to have some shock cord up there too. So let me put shock cord up there, tubular nylon, another 12 feet of that or so. 12 feet. Place that approximately the same location. Close. Let's fly it. New simulation. 72 inches here. 10-mile-an-hour winds. Simulate plot. Okay, so here's some things I noticed. First of all, I noticed it comes down fast under one parachute and then slower under the second parachute. That's good. I noticed that it drifts over 2,000 feet away. That's not so great. And it goes to 1,700 feet. That's probably okay. And it hits the ground at 18.2 feet per second. I'm okay with that. This is just the beginning, okay? So frankly, your model should probably have more details than this, but including realistic weights inside the av bay, also more bulk plates on the either end of the av bay, which I haven't put in here, and stuff like that. But this is how you handle simulating a rocket. I'm going to save this rocket. I'm going to call it sample rocket or something, and then I'll post it. And I would suggest that you start with this. This is not right, but this is on the right track. And you probably want to crank down the weight in the av bay and watch out for stability as you make it more realistic. Maybe your fins are going to be, in fact, your fins will be different than this because I didn't even look at the rocket, the real rockets when I drew these fins. I just kind of guessed at it. Okay, so this is Open Rocket. There is material available to read up on Open Rocket. I posted a document that was Open Rocket instructions from 10 point something. And it's like, I'm not sure that's even the most recent one. You might want to, when you get Open Rocket, maybe look for Open Rocket instructions and get somebody on your team to learn about Open Rocket. Coming up on the end of our time together, I would be happy to entertain questions if there are any. I see some people have been writing into the chat. So people, yes, center of gravity, that's a problem. 3 times worse than you want. That's a big problem. It's gonna drift, yes, indeed. Comments or questions right now? I have a question for Duluth. Did you not receive your package that should have come to you more than a week ago? Max got it.
Yes,
Okay.
yeah.
You got it. Good.
We just found it today. Thank you.
Very good. It turns out that I have not yet heard that the altimeters have come in. Unfortunately, they were supposed to be in more than a week ago. I need to check on that again. I was planning to teach about altimeters next week, but if we don't have altimeters in hand, that will be harder. Not impossible, but harder. So I'm going to find out if we're going to have them in hand by next week, and if so, I'll stick with my original schedule. And if I don't have altimeters in hand, but I'm pretty sure I'll have them by the week after, I might switch the last 2 lessons and do painting discussion next week and altimeter discussion the following week. And if altimeters cannot be had, which is actually the case for most companies right now, we'll talk about altimeters even without having them in hand. We'll describe what they do, we'll describe how to wire them, and when we get them, we will wire them, but we won't be able to have them in our hands while we're talking about it. So let's see. Did you get a chance to look at our build tables? And I will let Sophia said yes. I have tried to give everybody feedback. If you didn't hear back from Sophia, ping her again, please. Any other questions? Okay, so that's it for tonight. Send us questions anytime, of course, and check Sophia's build slides. They are impressive. They are bigger than they used to be, and they will continue to grow. The assembly of the av bay. Okay, so here's one thing you actually do need to do. You have to put a sled into your av bay onto which to mount your electronics. There was not one provided with the kit, strangely enough, and I didn't provide one either. So you'll need to make yourself a sled, some sort of a flat plate that can attach to the threaded rods. We'll talk about that when we talk about av bays, but you might want to be thinking about that even now, or read up on what those av bays could look like on the inside and get working on that. That's a part that I didn't give you and you will need, so you'll need to figure that out. Ultimately, once you have that piece, probably a piece of wood, frankly, then you can screw things to it, including the electronics, or glue things to it as necessary. More details on that later, but building your av bay sled is something to put onto your build schedule.
Excuse me, I have a quick question. Do we need to have the sled built first in order to start working on the av bay for the electronics? Or should we just start on the electronics and then build the sled later?
Well, basically the sled is what the electronics will sit on, but you don't have the electronics, but you do have the av bay. So frankly, you can assemble the av bay, and frankly, you'll see that it's 2 ends and a tube and nothing to put electronics on in the middle. So you want a sled that sits on those 2 threaded rods. So you can assemble the ab bay without the sled, but frankly, you can't actually build or finish the ab bay until you have the electronics, until you have the sled. So I'm just saying, why don't you think about what that sled could look like?
Okay, thank you.
Yeah, Kelly makes a point that putting the ab bay together is all of half an hour, right? It really comes together quick. You don't have to build very much except for the missing piece, which is the sled. And if you have a sled, we'll talk later about how to organize things on it. It's not just willy-nilly. There are rules about what goes where and what has to face up and what has to face down. But we don't have very many things to put into our ab bay, so it won't be hard to abide by the rules. We'll talk about those rules later.
Okay, thank you.
You do have to epoxy the couplers together, that's true, and you do have to epoxy the end plates to each other, that's true. So that will take a little drying time, but those are 3 epoxy joints, all of which could be done at the same time because they're not touching each other, if you wanted to. Anything else from anybody? Okay, I'm going to save this document and post it, and I will look forward to talking to you next week. Good night.